and welcome to the third episode of the PQC podcast. We have once again Raymond joining us. How are you, Raymond?
Good.
That's good. So just for a bit of background, in case you haven't watched the last two episodes, I'm the co-founder of XeQuantum, a post-quantum cryptography startup that helps businesses adopt post-quantum cryptography essentially. So as quantum computers become more and more of a threat to current security, so does cybersecurity need to adopt. And that's why thus governments all around the world have recently standardized algorithms that can withstand quantum computers. Raymond here is CSIRO, a PQC researcher, who has developed his own algorithms and has improved on existing algorithms, making them faster even than the current classical encryption methods. So, without much further ado, we can proceed to our subject of today. Today we'll be talking about AI and hardware and how they're related to PQC, some advancements, some things around them, and some interesting facts a bit personally speaking. So maybe we can start actually with a bit more of a recent development. The CEO of NVIDIA, I believe, has recently commented on quantum computers and said that he doesn't believe that very useful quantum computer will become a thing, essentially, in the upcoming decade. He said that it's most likely going to be around 20 years, and that has caused stock of quantum computing companies to go down by 50% at some points. So we'll be starting today by talking about such comments, whether it's true, whether it's not true, and what are the implications of such comment. So Raymond, maybe you can take it away and tell us a bit about what your opinion on his comments are.
Yeah, sure. So first, a disclaimer that I don't hold any stocks in those quantum computer companies. Whose price just plunged a few days ago. So okay. So I think regarding these comments, I think it pretty depends on what is your application. Right? Like if you think about so whether a quantum computer can just do like my daily office work, like what I can use on my classic computer, then probably yes, it will be like in about 20 or even 30 years. Right? However, the quantum computer is really good at doing a few things. Like, for example, breaking public key cryptography. I mean, classical public key cryptography is one of them. And also, like, there is also like the quantum key distribution, which is informational secure, right? So, and also, like, from what I heard from my colleagues who is doing like quantum AI, quantum machine learning, quantum computer could give like those machine learning AI algorithms a big boost on the performance. And actually, it is not really just in practical for those quantum machine learning or quantum AI algorithms, because they can, for example, run those algorithms in some simulators. And right, for some simulators like the IBM Qiskit, if you pay for the plan, then you have access to the actual physical qubits. And from what I heard from my colleagues, that you can even run some of the algorithms with just a few qubits. So this is not that practical. Actually, it is really practical, I would say.
So basically, you could what you mean by very useful depends on like whether it's true or not. That comment depends on what very useful means. Maybe we will not have a quantum iPhone that I can go to the Apple Quantum Store, and buy the Q iPhone in the next decade. Maybe that's true. However, there are already applications, commercial applications you mentioned, especially around AI and security, that can be applicable already today. And in the upcoming years, it's just going to get better and better. Is that correct?
Yes. Like, for example, in CSIRO, we already have a lab which has like two quantum key distribution devices. Then they can already just do the secure communication that is informational secure.
So quantum key distribution is already a thing. It's already been implemented, maybe not at scale, but it's already been proven to be real. And as we know, the difference between proof of concept and scale are much smaller than nothing in proof of scale. So do you think it's very likely that in the next, say, 5 years or 10 years, quantum computers will be able to break current cryptography and will have a quantum key distribution center? According to Gartner, 2029 is going to be the year that we all have to be prepared because it might happen on that year. What is your estimation?
I think my estimation is also like around 2030, but everyone need to be prepared because there may be a breakthrough in the quantum computing before 2030. And I think we have already discussed this in previous episodes a few times, right? Because of now the decrypt later kind of attack. So you need to make sure that your data is protected against quantum computing.
Yeah, so essentially, it might be 5 years from now. It might actually be less. For all we know, Q-Day, as I say, is almost definitely a lot closer than 10 years. Things have been moving faster and faster. I think we have trouble understanding exponential growth and what it means. It feels like nothing now, tomorrow is everywhere. And like you mentioned, we have discussed it in previous episodes. I would agree that it's also important to reiterate it because there's types of comments like quantum computers are very far and we don't have to worry about it now are also being repeated everywhere. And I think it's quite important that we try to spread the information as much as possible because comments like these, or just like a lot of comments around, like for example, when the Chinese university broke RSA 50, everyone started going around saying, well, it doesn't mean much. If we keep going at that, if we keep saying it doesn't mean much now, then we are not preparing for when it does, because we are not taking it seriously enough. With post-quantum cryptography, this is one of the most catastrophic, potentially speaking, ignoring of development, because we are talking about so much data. We're talking about social media, for example. We weren't really prepared for it, or the internet. And now it's causing some societal problems because we were not ready for it, especially around kids using social media. We haven't been preparing for AI much. And now we're talking about the impact on the workforce, how AI is going to be replacing people, or people who use AI will be replacing people. In either case, it's affecting the workforce and there is no question about it. Maybe we should learn a lesson, especially around quantum, because the results will be a lot more sudden and a lot more catastrophic if all of the identity, all of the trust around data security, around identity, it's just going to be completely crumbling. Literally, one of the foundations of society is trust. And if you don't know who you're getting the email from, or you can't trust, say, your cloud, your iPhone to store your images correctly, like securely, and it might leak, you're not going to do either. You're not going to communicate. So I think around this, we're actually much better off acting like the sky is falling, as they say, well, than just trying to be conservative with the estimates. Well, I think we had a good. Is there anything you wanted to add on that before we go on to the next segment?
No.
Now that we talked about that, we can move on to our topics of today. So NVIDIA is both an AI and hardware company. And that kind of ties into our subjects of today, hardware and AI. Maybe we can start with AI. Fun fact about AI, one of the most receptive sectors to the solution of PQC, the one who has been most willing to adopt it, has been AI companies. They have been the ones who have been approaching me and requesting changes. I'm sure it changes when you talk about the public sector or enterprise. But when it comes to the private sector and non-enterprise, they're the one who are most interested. Raymond, do you have some theories as to why that's the case? Do you find that surprising, or do you think that completely makes sense? Especially considering places like healthcare who should care don't care half as much.
Yeah, so I feel this is a bit surprising, like you mentioned, right? For those who really need to protect the sensitive data, then they don't really care about. But for AI, I think it is not that surprising because there are some privacy-preserving AI techniques which have already actually been implicitly using PQC, like the fully homomorphic encryption, right? So if you use those fully homomorphic encryption libraries to program your privacy-preserving AI, then you are already using PQC, actually. So I think maybe people working in AI may have higher awareness of PQC if they have heard about fully homomorphic encryption.
So when you say it's already encrypting their data, do you mean the training data? Can you maybe go a bit more about what is homomorphic? Maybe you can expand a bit more. What does it use? What is it encrypting for AI? Is it encrypting the data? Does it do end-to-end encryption? Why would they still require potentially post-quantum cryptography? From my experience, the most that they want is a TLS integration, basically securing the session. Would the homomorphic encryption take care of that as well?
So what homomorphic encryption will do is it can do some algorithms on encrypted data. So, for example, if you have already encrypted two values A and B, then if you want to compute like A plus B without decrypting it first, then homomorphic encryption can just do like, for example, addition on two ciphertexts. Then the result basically is the encrypted value of A plus B. Why this is useful in AI is because for many AI applications, you develop your machine learning algorithms on the cloud, right? Then you don't want the cloud to know what is your data actually. Then in this case, the client can do is can use homomorphic encryption to encrypt the data. Then they send this to cloud. Then the cloud run this machine learning algorithm program by using this homomorphic encryption schemes. After they run this algorithm, then basically the machine learning algorithm can still work. However, the cloud will not know what is the actual data actually being learned in this case. So I think this is one type of the privacy preserving machine learning or AI.
Interesting. So it's basically an encryption that kind of maintains its state even after being altered, so that when it's decrypted, it's still the same state. And that's useful for when you want to train data, store it, but you don't want the cloud service to know the data that you've been storing on their device.
Yes.
Do AI services generally employ that? Or maybe that's what they are looking for when they look for services? Like, is that widely adopted?
I don't think it is widely adopted at the moment because from what I know, the overhead of running this homomorphic encryption algorithm is pretty high, even like GPU accelerators.
So maybe to some degree that's what they are looking for. They want the data that they use for training to remain private from the cloud service, from potential hackers. They want their chat session secured as well, because to some degree that's data communication. There could be some reasons, and there are basically two big reasons that they would look to be more proactive on PQC. One, their data is their IP. It's their unique selling point. If their data is leaked, there is no company. Because that's basically what their main selling point is. Another one that I think, I'm not 100% just based on my experience, is they get more scrutinized than other companies. Wrongfully so, in my opinion. Healthcare companies, for example, hold identity data that is very sensitive. However, people don't generally ask, probably because they're a bit older. Health has been here forever, and they've been maintaining data forever. So we kind of just assume that they adopt with the time, even though apparently only recently has it been regulated that they even have to encrypt their data, because apparently a lot of healthcare companies don't encrypt their data classically, let alone post-quantum. But AI companies, everyone knows about their data, the effects that they handle data, and the first question people ask is, what do you do with this data? How do I know that your data is safe? And there have been some AI companies whose data has leaked, like the user sessions or the training data. People's sessions get leaked. It feels very privacy invasive, essentially. So they get asked more, and therefore they feel the need to adopt post-quantum cryptography, which is not a bad thing. Someone has to lead the way. And I think if there is one sector adopting it first, then everyone else will adopt it later. I mean, everyone is adopting AI to some degree. Companies that adopt PQC AI are more secure, especially if the AI starts handling their data, etc. Because a lot of the data will be stored in the AI. So it's not necessarily a bad thing, but it's just something interesting. Do you think that there is some relation between PQC and AI? Because I've been asked many times, is post-quantum cryptography able to withstand AI-powered attacks? Is there some relation between AI and brute forcing or AI and decrypting keys that PQC can either help with or maybe is actually vulnerable to?
Actually, this is a very good question because in July last year, I attended a workshop in South Korea, and it is about AI and cybersecurity. And one speaker who is an expert in this area And actually, yes, because AI is more powerful to break cryptography in some way. For example, there's like differential attack, right? So what differential attack is, for example, if I encrypt 0 or encrypt 1, then without knowing, any information, then I can just make a 50% guess, right? Then basically I have like 50% chance to guess what is the plain text correctly, right? However, if you use AI to do the differential attacks, then you can somehow basically increase this chance to 50%, right? So yeah, so the AI actually is really good at this kind of differential attacks. And actually, there are already like some improved attacks using AI on breaking symmetric key cryptography, like AIs. Although AI is not broken, but what I mean is they break like more wrongs than without AI. There's also the side channel attacks, right? And for many side channel attacks, it is also based on this kind of the differential attacks. You have you collect the samples from two like signals, then you want to know which one is, for example, encrypted 0 and which one encrypted 1, right? So you want to do this kind of differential attacks, and AI can also help that. And from what I learned from such speaker in South Korea, with AI, basically probably make some kind of sectional attack. For example, one type of countermeasure is called masking. So basically, you can, instead of like you just compute the value divided, now you have like two shells. Then basically you do like some kind of secret sharing in this way. Then if you only have two shells, then probably AI can pretty much break it. So basically, so you need to have like more shells, the higher level of the masking countermeasures. So basically, you can see that AI is really powerful in breaking cryptography, and I think probably with AI, at least I don't know how AI would interact with like the quantum attacks against cryptography, but for if with AI, it can pretty much help the sectional attacks. That's what I know, even like against the POC.
So if I'm understanding correctly, AI is able to infer vulnerabilities and find things that are like patterns, etc. in the encryption, and able to logic into guessing. It's increasing the chance of it guessing it right, because technically, what is decrypting if not just guessing? I mean, decrypting without a private key. Trying to decrypt by hacking is basically just trying to guess the correct original data, and the AI can really help with increasing the chance of breaking it, sadly. And from what I understand, it's not known yet where the PQC is going to be helping, or is how it's going to be interacting with AI at this point. Is that right?
Yes, because for this kind of task, this is more breaking symmetric key cryptography, like trying to break AIs. I think for sectional attacks, it is also applicable to POC, right? But I don't know whether AI can help like doing this kind of differential attacks on MLKM. I'm not sure.
I mean, attacking symmetric keys is kind of circumventing the whole MLChem, because MLChem relies on creating a shared secret, a shared symmetric key. If the symmetric key is the one under attack, then AES, for example, which is supposed to work in tandem with MLChem, then it's not that it just beats PQC per se, it's just that it's kind of circumventing it. It's in an area that PQC haven't been, well, that the mainstream PQC haven't been dealing with. I've heard of some solutions around there that kind of try to make a more difficult symmetric key. I've seen some that have been compared to AES 512, like in terms of strength. I do know that increasing AES key is not always better. So I assume that they mean if it was better, it would be like that. Would you say that those new types of algorithm might be able to do better against AI attacks? Or is it just a whole new area that we need to look into? Because, I mean, AI is young, really. Like, the practical AI is young. And so is the new era of cybersecurity. So we just kind of have to research and look into how it will all unfold?
Yes, I think using AI to trying to break POC is not well started yet at the moment. So I cannot really comment on this because actually no one knows, no one on the earth actually knows about whether AI can help breaking POC or not at the moment.
Well, I guess the hope is that we'll be able to we'll be able to find out how to protect before how to hack. I mean, technically that's what we're doing with PQC. We're learning how to protect from quantum computers, theoretically speaking, before quantum computers are able to hack. So hopefully we can learn how AI is able to hack and how to protect from it before we can actually start hacking. It's basically another area of cybersecurity that's being created right in front of our eyes. Potentially AI might be able to be used to help with cybersecurity, just like how quantum computers can help with cybersecurity, as well as hack it. So it just the technology side of cybersecurity coming to view again. We are back. Whether we like it or not, the tech side of cybersecurity is no longer invulnerable as it used to be, and now we have to adopt from all kinds of directions. That's a bit of a scary thought, really, that now this war is beginning again, because with RSA and elliptic curve being able to basically take care of everything for us for decades, we hope that it will be the end, but I guess that's not how life works. If we are already talking about different sectors and the application of PQC, another interesting one that is in the works is hardware integration of PQC. It's actually kind of unprecedented. There is a quantum random number generator that has been applied by different companies. For example, I believe Samsung has done it recently, and Apple is working on it. There have been a lot of quantum random number generators coming out. However, it's still a researched one, like in terms of the actual application of the algorithms themselves. It's a researched area. No company has actually finished doing it and started manufacturing, say, a quantum secure phone. Actually, one of our clients is a phone company, and we are working with a potential research into hardware PQC. And apparently the governments offer open to grants around it because it's just such a new area. And there's a lot of opportunities and a lot of secrecy. Raymond, can you tell us a bit about what you can tell, at least, about this, about some, if you know of any interesting development, or how it can even be done? Like, how is it going to work the same way as software, or is it going to be a whole new area, like AI almost? What are your thoughts?
So I think for hardware, it is important because you probably have heard about the hardware security module, or HSIM. So I think nowadays almost like every company is making hardware chips. They are trying to develop their POC HSIMs. Because for HSMs, they are used in many areas, like in finance and in defense, actually in many areas, and also for the government critical infrastructure. Basically, for hardware, I think it has a few more challenges compared to the software development. We have discussed a bit about this in the first episode, because for POC, it's basically require more computations, higher memory consumption, larger key and subtypes was initial size, right? So if make the development of the POC algorithms and the the keys, the subtypes was initial on this kind of hardware, especially on some very low powered embedded devices, more difficult. And the other thing is the cryptography is another big thing, because for hardware it is harder to do the firmware update than software. Unlike, for example, for your Windows 11, you can just click Windows Update, right? For hardware, it's very hard to do the firmware update, right? Because, for example, many of these devices, they are developed in hostile environment. Many of them, they in the IoT devices, they are just the sensors. Right, so then they are for this kind of things, it is more difficult to do the update. Right. So, and I think, yes, so these are some, more unique challenges to develop PQC on hardware. And this is also a really quite actively research area at the moment.
Yeah, I mean, we talk about crypto agility. Hardware and agility are kind of antonyms, aren't they? How are you supposed to update hardware that has already an algorithm implemented? We're going to have the mechanics go around, just be like, I'll have a look at your iPhone, I'm going to have to take it and update it. It's definitely a trickier area, and like you mentioned, they have to work around the different computations, different key sizes, different signatures. Hardware is a lot less flexible, I imagine, than the application layer or the software layer for that. So overall, it sounds like it's just a lot more of a hard area, if you will, than the software. Do you think that overall it's even is it going to be even viable to adopt crypto agility? Do you think there'll be a way to work around it? How does the algorithm get integrated into hardware? Do you just use assembly to do those algorithms, or is it a different type of work altogether?
For this kind of hardware programming, you usually have quite specific languages like Verilog or FDL. I think, for example, if you have the FPGA, you can use these hardware programming languages, then try to run this. Right. So this is how the hardware programming usually works, and also after basically you get something useful, then you need to do the manufacturing, right? So yeah. So regarding the update, I'm not sure because I'm not a hardware programming expert. I'm not exactly sure how they are handled at the moment. I assume that they, for some of them, if they can run some kind of software on your hardware, I mean, it is not hard coded, then you may be able to do the software right by, for example, maybe the network or something. But for those hard coded ones, then I guess probably you need to just use the mechanism to replace the hardware itself, right? That's probably more difficult.
Yeah. I think that hardware is not as much of either of our area, so it's a bit trickier for us to make comments. But it is definitely an interesting area, especially considering how heavily research that is. Apparently, Microsoft and Apple and Samsung and a few others have joined a collaboration just to do research around that. The quantum random number generator being integrated sounds like that's a bit easier to do, and that can be helpful, I can imagine. What would be interesting for me to see is, I think what you had in mind is an interesting idea, that maybe if we can I'm not sure, don't quote me on this, because it's, as you mentioned, we're not hardware experts, but if there's a way to make the software a bit lower level, at least affect the lower level more, maybe then we can, or make it more malleable, maybe that would be the best way to integrate crypto agility. Maybe quantum computers, quantum chips, and all that can actually play a role in that too. A quantum random number generator that can be integrated into the phone already utilizes quantum mechanics. Maybe there would be a way to actually integrate a bit more quantum mechanics, such as a quantum key distribution, which from my understanding is going to be more hardware level anyways, to establish communications. How is it going to be done on scale? That's a whole nother question. But I suspect that's what's going to be the end goal for, say, the communication between my iPhone and the tower, communication tower, might need to utilize quantum key distribution, because utilizing PQC will not really be very aligned with crypto agility for the hardware level. It just might be too difficult. Does that sound like a logical conclusion to you, or do you think I have no idea what I'm talking about?
From what I know, right, the current quantum key distribution devices, they are still quite large, right? So they are still a big boss. You can just imagine this is the fourth generation of the classical computers, right? This is to take a whole room for the fourth generation of classical computers, right? But I can't imagine that it will become smaller and smaller. From what I heard, there is a company in UK, they are already making this kind of chip-based quantum key distribution devices. So basically you can run quantum key distribution with more chips. Although I think for some other things, maybe the receivers, for the photons, then for those kind of things, they may still take a bit space. But at least for the core mechanism, they can already run this on a chip. That's from what I know. I think this one thing, and the other thing is also related. This is also related to the hardware updating issue we discussed previously. And I think the cloud-based solution may be more viable, right, compared to develop POC algorithms on every hardware, on every devices, right? Maybe the cloud-based solution is more viable because first it is probably easier to do the update, right? So it gives you better crypto agility. And the other thing is you offload this computational overhead to the cloud, right? So if, for example, your hardware is very low power, the embedded device then can still run this POC algorithm, which it has more computation than some of the classical public key cryptographies.
Whether QKD or PQC is the future of hardware, I think we can agree that the most likely scenario for either is hybrid. In case of the hardware, there will be a hybrid of software and hardware, where the software handles the computations and the hardware handles the values that they get. Because that way, crypto agility can be integrated, essentially. It might introduce some latency, I can imagine, necessary for... If the phone is not connected to the internet to begin with, then it doesn't need that type of thing anyways, generally. I do feel like you mentioned, quantum key distribution is getting smaller and smaller. I feel like we'll get to see QKD integrated into smartphones way before we have quantum smartphones, because this is just the most advanced area in the quantum area at this time. And from my understanding, quantum key distribution is more for hardware layer anyways. PQC is more for application layer, software layer, and QKD is more for hardware layer, lower layers. Neither is meant to replace the other, per se. Is that correct?
Yes, like you mentioned, right? So we probably need to have this kind of hybrid mechanisms, right? Because the thing is now basically you have like 3 different kind of cryptographies, right? You have the classical public key cryptography, you have PQC, you have QKD, right? They all based on different hardness assumptions, right? So if you put them together, then instead of if for example one of the assumptions is broken, then the whole thing is broken. Now if you make different things together, then basically now the attacker need to break 2 or maybe 3 of them in order to get the encrypted data, right? So yeah, I think for this kind of hybrid mechanism, it is important, and it is also quite actively studied in academia. And actually, we had 2 papers recently. One has already been accepted by a conference, and the other one is currently still under review. So basically, both of them are doing this kind of hybrid mechanisms, but in a more efficient way.
Nice. That kind of seems to be the upcoming future for a lot of things, hybrid. You get the best of both worlds, or try to get the best of both worlds from 2 things that cannot be handled on their own. I think we're coming to understand sometimes that some things are limited, and we just have to accept that rather than try to make it better. One thing that comes to mind is a lot of AI companies just try to increase more data, try to increase their computers. Not gonna make names, but already have massive servers, and their AI is not improving, so they're like, well, we need bigger servers. Let's raise $1 trillion. Like with the upcoming new technologies, we're gonna be mixing and matching and eventually getting the best results out of everywhere. And this, of course, also applies to security. It's an interesting era we are arriving at, and I think definitely we'll just wait and see and continue working towards a more secure future. So at the very least, whatever happens, we don't get our identity stolen. So thank you very much for attending. That was the 3rd episode. I mean, I was thinking it's going to be 1 hour long episode. This ended up being very fruitful. 3 episodes, 40 minutes each, 40 to 50 minutes each discussion. So I really appreciate you taking all this time to come on board and chat. And I mean, I would love at some point, like if there are any more like topics that people want to talk about or that we can think of, would love to do this again for maybe a 4th episode. Is there anything else you wanted to add before we finish?
So I think just maybe a closing statement. So for this kind of PQC or quantum safe migration, this is very fast emerging. The development on both PQC and quantum attacks on classical public key cryptographies are very fast. You can see, right? Basically on every episode we discuss some new comments from some companies or some big name persons, right, in that week, right? So you can see, right, it is really fast moving area. So because it is fast moving, it's better to be prepared now than later, right? Because maybe tomorrow, for example, China make quantum breakthrough, right? For example, China maybe say, okay, today we break, I say 128 or something, right? Then tomorrow we break, I say 256, right? Then you can see, you don't know, right? When I said will become totally insecure, right? So that's why. So I think we basically need to start to plan the quantum safe migration now.
Yes, I agree. Things are moving crazy fast when you think about it. While we were planning our first episode, I think that's when the Chinese breakthrough happened. Between our first and second episode filming, Willow happened, and between our second and the third one, the comment made by NVIDIA and a few more algorithms came out. A lot of things are happening every single month, essentially. And it's going to speed up in what's being called the year of the quantum by the UN for 2025. So it's definitely very urgent that we are ready for this. Quantum computers are going to change at least as much as AI, and it's going to bring about a very exciting future. However, everything comes at a cost, everything comes with side effects, and we need to make sure that we learn a lesson from history, and we are ready for the side effects of new technologies, and so that we can utilize the better side of them the best that we can. And who knows where next we go with quantum computers, especially once they merge with AI. So once again, thank you very much, Raymond, for coming on board, and thank you for watching. If you watched this long, there will be more coming with various topics coming. There is no end, honestly. But thank you very much, and I'm looking forward to seeing you next time.
Right.
Bye.